Hello and welcome to our next lesson of periodic functions, where today we are looking at the sine function, and we are going to be learning how to connect sine ratios. So from the trigonometric ratios that we saw, specifically with the sine and connecting it to the sine function with regards to its graph, as well as to describe why this function is or why this relationship is actually a function. Well, what is the sine function? The sine function is the graph of the function f of x, where the output is defined as sine of x, where x can be any real number. So x is an angle, and we are only working with degrees, so the measurement will be always in degrees. There is also radians, so I am going to briefly show you if you are using graphing tools, how to distinguish between those two so you can get the correct graph. And of course, this is a periodic function. So I'll be showing you specifically for Desmos, but any other graphing tool that you use as well, you just have to make sure that the setting is in degrees. So here, of course, I can put sine of x, and it will automatically evaluate this for me. But as you can see right now, which is the default of Desmos, this function goes from 0 to, as you can see here, 2 pi. And this is actually another measurement for angles, which is radians, which we're not going to be using. So I will just select this to be degree, and I can already see that this function has changed here. So let me show you on here. So if my x is set to show until 13, I don't really see any values there. But if I expand to greater values, so I put 720 or as follows, you can now see these correspond to the degrees, which is also what we expect. Sine of 0 is equal to 0, sine of 90 degrees is equal to 1. So now, this is the sine function as we see here. And pretty much it is we are evaluating the output as sine of different degrees, so or different angles measured in degrees. So as mentioned, we have 0 degrees, 90 degrees, 180, 270, and 360. So one complete cycle of this function goes from 0 to 360 degrees, or the period we can say is 360 degrees. So on this graph here, I've shown you the negatives as well, and then here we go until 720. So this is 3 cycles of the sine function. And so just so you remember, the period is the horizontal distance over which a sinusoidal graph completes one full cycle before repeating. So again, in this graph, this is 360 degrees. And again, this is just the parent function. Later, we're also going to see transformations of the sine function, which will affect the properties that we are going to see as well. Now, another aspect of the sine function is also the equation of the axis. And this is the equation of the horizontal line, which is halfway between the maximum and the minimum value. And of course, it's the average of the maximum and minimum. So in this case, and again, looking at just this one cycle, and maybe let me highlight this for us here. So we're looking at this cycle here. And the maximum occurs at value 1, and the minimum occurs at -1. So the horizontal line that's halfway between these is actually the x-axis in this case. And the equation of the axis will also be the x-axis. So it will be y is equal to 0 in this function here, or in this function here. Next, we also have amplitude. So amplitude is the distance from the function's equation of the axis, so from that middle line, to either the maximum or the minimum. Now, because this equation of the axis is the halfway point, it doesn't matter if you look at it from this line to the maximum or to the minimum. This distance is 1, this distance is also 1. So the amplitude, regardless, will be 1 in this case. And finally, a sinusoidal function is a periodic function that is obtained from the transformations of the f of x is equal to sine of x function. So, of course, this function itself is considered a sinusoidal function, but later when we see any transformations of this, and remember we can do stretches, translations, or reflections, all of those will be sinusoidal functions as well because they have that sine in the output. Now, consider this graph here, and this is actually a periodic function here as well, because remember, it is repeating, one portion of it keeps repeating. So first, label one period on the graph, and you have different options, so it depends on how you are looking at this. It is always suggested that you start from 0, so I can consider or this portion of it as 1. But you can also choose to look at it perhaps this way. This is also uh, the portion of the function that keeps repeating. But regardless of which way you look at it, the how much the period is will still be the same. So first, let's look at this one. And in this case, we can clearly see 1, 2, 3, 4, 5, 6, 7, 8 units. So this will be 8 units. Or even if you start with this part and then go upwards, this is also still 8 units. So it is important for you to know how you're defining one cycle because you need to know which part is repeating. Clearly, we can see just from these two, I can't have this and this as one cycle of the same function because then I have this piece in the middle that won't belong. So either I have to go with this pattern for the repeating pattern or this one, or you can even choose, for example, to do something like this. This is also could be considered one period and it is 8 units. But again, just to keep it general, it is recommended to start from the x is equal to 0 and work your way from there until the next repeat, which occurs here. And then this is one period. So I'm just going to erase this and we're going to keep just that basic one. Now here, what's the maximum and minimum? And we have to label on the graph. So the maximum, of course, is here. And maybe let me draw with this one. This is the maximum and it is equal to, and we're just counting up here, this is 4. And the minimum is actually here and it is equal to 0. And so in this case, we don't have any negatives, so my minimum will just be there. And you can also have, if this was translated upwards, then your minimum would also be a positive integer. So you just have to look at the minimum point on the graph. And now draw and label the equation of the axis on the graph. So the equation of the axis, remember, is halfway between the maximum and the minimum. So y is equal to 4 plus 0 divided by 2, which is just going to be 2. So then it will be this line here. And typically we do this with a dashed line as such. And I can label this as y is equal to 2. And now, what is the amplitude? And the amplitude will be from this line either to the maximum, so this is 2, a distance of 2, or from here to the minimum, which is also 2. So amplitude is 2 units in this case. Now, in the next graphs here, I want you to think which of these situations are modeled by a sinusoidal function and why do you think so? So first we have the height above the ground of a person on a Ferris wheel. Then we have the depth of a programmable radio-controlled toy submarine. And finally, the motion of a flagpole in a gust of wind. And these are the corresponding graphs as well. So here, the way we match it, it is in the same order, but if you weren't sure, here we have height. So this is height and time. Here we have depth and time. And finally, distance from the vertical. So consider a flag that's that's blowing in the wind. So it is the distance from the where it starts. So already I can see this one is not a sinusoidal function because it's not even a periodic function because the shape is changing. In this one, also, the graph, yes, it is a periodic function in the sense that there's a cycle that keeps repeating, but it's not that shape that we saw from the sine function here. Remember, transformations of the sine function are translation, stretch horizontally or vertically, or reflections. But really, you are going to end up with this shape, just again, stretched or reflected or um, maybe moved up or down. But in this case here, this is a whole different shape. We have many maximums or different maximums and minimums depending on which part you're looking at. So it is not that consistent shape. So this is also not a sinusoidal function. However, this one, it is the pattern of the same shape as the sinusoidal function or the sine function, but it may have just been translated or it may be stretched because we're considering height on a Ferris wheel, so it might be greater. So this is the only one in this case that is a sinusoidal function. And again, it has to keep that shape, which neither of these two do. And it does have to be the same shape that's repeating periodically. And this one certainly doesn't have that either, even though it kind of does look like the sine function, but it is not consistent throughout. So only this first one is a sinusoidal function, which corresponds to this one. And we are going to actually see a lot of examples with Ferris wheels. So we'll see how we can connect the sine function to the movement of a Ferris wheel. Now, these are the same properties that we just talked about, but I'm only showing you for one cycle of the sine function. So again, we start from 0, and any of these points that you look at will correspond to the sine ratio for the angles with these measurements from 0 all the way to 360 degrees. And of course, we have our maximum, which occurs when we have an input of 90 degrees and sine of 90 degrees will be equal to 1. And our minimum occurs at 270 degrees with an output of -1. And y is equal to 0 here is that equation of the axis. So equation of the axis. And so we can clearly see the amplitude, either considering the maximum or the minimum, will be equal to 1. And this whole part from 0 to 360 degrees is one cycle, and this is the cycle that keeps repeating. And so, similar to one of our previous examples, any multiple of 270 will have this output of -1. Any multiple of 90, well, not any multiple of 90, because 180 will be a multiple of 90, but rather every after every cycle is done and you go another 90 from there. So how we would write it is we would say 90 degrees plus 360 degrees times n. So for example, after one cycle, you have 360 and then another 90 would bring you to 450. So at 450, you will also have a maximum of 1, or multiply by 2, 3, and so on. And now we're going to uh, see some of those values there as well. So you bring out your calculator here. We're going to calculate some of these values. And these are some of our common trigonometric ratios for sine as well. So it is good to get familiarized with these. So of course, sine of 0 we know is equal to 0. Sine of 30 will be equal to half. Sine of 45 is square root of 2 over 2. And we are keeping exact values here because these are the common values that we need to recognize. Sine of 60 will be square root of 3 over 2. Sine of 90 we just saw is 1. Now sine of negative 90, remember we are now working backwards. So if we were going this way, it's the same as if we were going this way from the cycle. So in fact, these two are not equal, and this one is actually negative 1. Now sine of 80 is 0, and 180 is different because when we work backward this way and go back 180, so if we had done this here, we would also still be at 0. So this is the one example here where we are going to see that in both the positive and negative case, it will be 0. Now, sine of 270 is also negative 1, which is our minimum here. However, sine of negative 70 could be, or sorry, sine of negative 270 can be interpreted as sine of 90 because it's this portion of the cycle that we're looking at. If we go, consider here, we go negative 270 backwards, so we're pretty much at this point here. Now, sine of 360 is 0, and sine of negative 360 is also going to be 0 because if you go backwards, consider this is repeated and you go backwards, you're also going to end up at this 0 again. And this is just due to the shape of the the cycle of the sine function. So think now, what do you notice about these values based on what I had just mentioned or just your own observations? What do you notice? And also, how do you connect these values to the graph of sine of x that's shown above here? And of course, as we saw from sine of 0 to sine of 90, all of these values were positive because we're going positive. And any value between 180 to 360, which we only saw this one, but any value that you calculate will be, or sorry, in this one, will be a negative value because we are below the x-axis. And of course, we saw the three x-axis, which occur at 0 degrees, 180 degrees, and 360 degrees. And keep in mind, this is still a function. So of course, we still have the x-intercept and y-intercepts that will be one of the properties of this function. So as mentioned, we have three x-intercepts here, and our y-intercept is the point 0, 0. Now, an application question for us here. Sarah is sitting in an inner tube in a wave pool. The depth of the water below her in terms of time is shown in the graph below. So we're going to interpret this graph in context of this problem. So first, I want you to just analyze it yourself and see if you can figure anything out from just looking at this graph. We're pretty much going to look at all of those definitions that we just learned, which are properties of this function, and interpret them. So first, consider the period, which is the change in time from for one cycle. So starting at, again, my time 0, I want to go until I get to that point again, and I make sure that at this point, this is repeating again. So I will draw a dashed line here for myself, and maybe I'm just going to change the color here. Let's do blue. So approximately here, this is one cycle. So this is about 3.5 seconds or approximately 3 seconds for one cycle, for one cycle there. And so the time it takes from one peak of the wave to the other is 3 seconds. You can also, when you're looking at the cycle, you can go from one maximum to another maximum here, and you'll see that one is approximately 3.5 as well, which is what we've written here. Oh, pick either two maximum points or two minimum points and consider the time in between. And so again, from we can consider that one wave up and down is going to take approximately 3 seconds. Next is the equation of the axis. So here we see that the maximum occurs at 2.4 meters and the minimum is 1.6 meter. So the equation of the axis will be the average of those two values. So y is equal to 2.4 plus 1.6 divided by 2, which is equal to 2 meters. And the interpretation of that is Sarah's height above the bottom of the pool in still water is 2 meters. So after a wave comes and then it goes, at the point where there's no wave, and Sarah is sitting still in the tube, her height from the bottom of the pool is 2 meters. So consider this is the bottom of the pool. This is approximately or this is actually the equation of the axis right over here. So if there was no wave, if there were no waves, Sarah would be just sitting on this line at 2 meters above the ground. And finally, the amplitude, which is here I found the difference between the maximum and the equation of the axis, so 2.4 minus 2, which is 0.4 meters. And this is the height of each wave. So when the wave comes and the water height rises, then it goes up by 0.4 meters. And also when the wave goes down, the water goes down by 0.4. So each time the wave goes down, Sarah's height goes to 1.6 meters above the pool, above the ground of the pool, and every time a wave pushes her up, she's at a height of 2.4 meters above the ground. And that is the interpretation of this graph, and that's how we also just saw an application of sinusoidal functions, as well as how the different properties can be used to analyze problems using the sine function. And that is it for our lesson today. So you have some practice problems to solve. As always, please check Google Classroom for additional tests, and don't hesitate to reach out if you have any questions, and I'll see you all in our next class.